Hi everyone, welcome back to the Cardioid simulation series, where we explore math and physics visually and interactively. In this episode, we are diving into a powerful concept, scalar and vector projection. This is the key to understanding how one vector casts a shadow onto another. Let's break it all down step by step with animations. Let's start with two vectors, a red vector called B pointing diagonally, and a yellow vector A lying flat along the x-axis. The letter B in vertical bars is called the magnitude of vector B or length of vector B. And the Greek letter theta is the angle between the vectors A and B. Now, if we drop a dashed perpendicular line from the tip of vector B down to the direction of vector A, this is called the scalar projection of vector B onto the vector A. This gives us a segment that tells us how much of B is going in the direction of A. Let's now derive the formula to calculate this projection. We know the cosine of angle theta between the two vectors is equal to the adjacent side, which is the projection, divided by the hypotenuse, which is the magnitude of vector B. We also know the dot product of vectors A and B is equal to the magnitude of vector A times the magnitude of vector B times the cosine of the angle between these two vectors. Substituting the value of cosine of theta from equation 1 into equation 2. Magnitude of B cancels out and we are left with A dot B is equal to the magnitude of vector A dot the projection. Finally, we isolate B. This gives us the scalar projection, just the length of the projection of B onto A. But it doesn't tell us the direction. To get the direction, we have to calculate what's called the vector projection of vector B onto vector A. Fortunately, that's very easy to do. Vector projection of vector B onto vector A is simply equal to A divided by magnitude of vector A dotted with the projection B that we just calculated. Now we have a vector that has the right direction, i.e. same as A, and the right length, i.e. the projected part of B onto A. Finally, let's see how vector projection changes as we rotate the vector B around. As B turns away from A, the projection shrinks because B is contributing less in the direction of A. At 90 degrees, the projection becomes 0 because B is completely perpendicular to A. This gives us a real feel for how direction and angle affect projection. That's all for this one. In the next episode, we will be building on these ideas towards simulating the beautiful cardioid pattern in a teacup and even the floating dandelion that we teased earlier. If you found this helpful, like the video, subscribe to the channel, hit the bell icon so you don't miss what's coming next. Thanks for watching. See you in the next one.